Ladies and gentlemen, hello and welcome back once again to the longest running show in the world about data. It's called DM Radio. Yours truly, Eric Kavanaugh here. And folks, I am super excited to talk about some of the coolest technology that I've seen in quite some time. I remember way back in college, I wrote my thesis for both English and philosophy on the same writer who was Edward Albee. And he wrote a play called The Zoo Story. And there was one line in that play that just jumped off the page at me, and I'll never forget it. He said, sometimes it is necessary to go a long distance out of the way in order to come back a short distance correctly. And I was like, wow, that's pretty cool. And then I start thinking in the context of data and information and files and moving things around. And goodness gracious, from the earliest days of DM radio, I recall asking people from companies like Informatica and IBM and SAP and all these various vendors back then. I was like, can you guys get a strategic view of what data is moving where at what time? And I was thinking mostly in the structured data world. Today, we're going to talk about unstructured data as well. I was thinking about structured data with all these ETL processes: extract, transform, or load, extract, load, transform. And the answer was always, huh? Like, what are you talking about? And I'm thinking to myself, that's got to be tremendously inefficient. I mean, so many times you're moving massive amounts of data that you're not even going to use. You're only going to use 10% of that or 20% of that. So there's just all this extra effort. And anytime you move data in these traditional ways, there are potential for errors. You can have truncated files, it doesn't load properly, you get performance issues, all kinds of reasons. And you think today about how incredibly heterogeneous and topographically challenging information landscapes are with all these different systems, operating systems, file structures, cloud, on-prem, devices. It's just crazy and it's extremely challenging. Well, the company we're going to talk to today, a couple different companies that work together, they have solved for this very problem. And the first time I learned about it, I was talking to the CEO, David Flynn, who's on with us today, along with Molly Presley, who does the Data Unchained podcast. And we also have Matthew Shaxted from Parallel Works, good Chicago boy like me. And I figured out they solved this problem. So the company is called Hammerspace, and then we have Parallel Works, and Hammerspace is the space from which magicians pull things like rabbits out of hats. So it's a very interesting concept. But basically, they came up with this structure for a what they call a global namespace to which you have access for everything in your environment. So there's an overlay that goes on all of your data sources. And now you've got this namespace where you can pull rabbits out of hats all day long and orchestrate your data. And when I heard that, I was like, wow, that is solving for so many performance challenges, so many annoying aspects, so much friction in the workplace when people are trying to do things, whether it's do analysis of videos or pictures, for example, or whether it's to train AI models. These folks at Hammerspace are training Llama 2, this giant large language model out of Meta. So I thought to myself, this is amazing. And I always love when companies solve huge, previously intractable problems in elegant ways because it's just a game changer. And there's going to be so much time saving and such a boost to morale for organizations that embrace this new way of doing things. But with that introduction, let me bring in David Flynn of Hammerspace. So did I get it correct? Is that about what you guys are doing?
That is a very good description, and I like how you talked about it as a long-standing, intractable problem. That actually
Right.
was part of my pitch going back. Is we're solving things that the industry has failed to solve for decades now.
Right. Well, for decades, and you think about this is the realization I had like 16 years ago. What happens with ETL and data warehousing? People figure out, hey, this is cool. I want to be able to analyze my data. Oh, let's get this data set in. Let's get that data set in. Now you have all these batch windows that are stacking up. Well, it used to be you could do them overnight. Then there were so many of them. Now you got to do it 24/7. So constantly you're moving data around. I even wrote an article about this on eWeek about data orchestration. Around and around and around it goes. Where it stops, nobody knows. It just keeps on going. And that's where I get that question about strategic views of things. Like you're probably moving the same data 2 or 3 times a week that you don't have to do. That data only needs to be there once a week, for example. And this
Mhm.
takes time, it takes effort, it takes licenses of the software to do things. And we we did a series a couple years ago, something like sunsetting applications and other fairy tales of the enterprise, because it's so difficult to kill an application once it's extant somewhere in the enterprise.
Yeah.
But I think you folks have the real potential to unwind this spaghetti mess of data movement and data orchestration in a very elegant way that improves productivity and it gets the morale high. No one likes to spend time waiting to get files and going, oh, where is this file? Why isn't it loaded
Nobody
yet?
wants to be a data janitor.
Oh, ouch.
And that's what I mean, that's what people are doing, janitorial work. It's a sin that the movement of unstructured data today is done so manually. It's, I mean, data
Yes.
is the very definition of digital, and yet it's crying out for digital transformation in how we map it and manage it across infrastructure. And yet those things are done piecemeal with, point narrow solutions that require expertise. And so I do think it's the manpower element that's the biggest savings.
Yeah. Yeah, and improving the morale, right? So that's one of my soapbox topics
Hmm.
is
hmm
when so
hmm
what hurts morale basically is when you feel like you're spinning your wheels, when you can't get things done, when people are demanding something of you. That's why data engineers or data janitors are pulling their hair out and wind up like guys like me because they have expectations put on them and they can't get the system to work fast enough. They can't get it to load
Or,
fast enough, to move around fast enough. That's really bad for business and morale, right, David?
or the fact that you just spent the last year and a year plus doing a data migration from some storage system to another. And what you have to look forward to is that in 2 more years, in 3 years, you're going to have to do the same thing again. And it's going to be just as painful, if not more, because it's more data.
That's a very interesting point, and you're reminding me of one of the funniest things that someone said on the show years ago. Said, in the IT world and the data world, we always think that just one more layer of abstraction can solve our problems. Well, in this case, it kind of can, I think. I mean, there are lots of details to be sorted out and lots of use cases to be understood or to be hammered out, so to speak. But I think that this particular layer, because you've created this high-speed conduit for data movement, unstructured and structured. It's like a super highway for information that anyone can access from anywhere in that incredibly dynamic environment, right?
Well, you're quite right. You can think of this as the missing level of indirection that we have never successfully implemented between data and the storage storing it. And the reason we never implemented it isn't for lack of trying, it's because you had to add an extra layer that indirects the data. You had to proxy the data.
Hmm.
So the key to having been able to solve this is actually moving to an architecture where you separate the control plane and metadata from the data path. And that allows you to have metadata served by separate control plane and the data path remain as direct or even be made even more direct than it was before to
Wow.
keep the performance. So, the problem is we had control and data, metadata, and data combined. Splitting them now lets us add that indirection in a way that doesn't compromise your performance and scalability. It actually unlocks performance and scalability.
That's very interesting. And then, last, I'll throw it over to you and then we'll bring Matthew in here. But essentially, we had sort of a two-lane highway, and now we have a highway that can expand out in lanes as needed, right? Isn't that the idea? Is that it could be an eight lane
Yeah.
or a 64 lane or 128 lane during rush hour, just
Well,
expand it out.
the analogy I like to use is that we have been living running on traditional surface streets, regular roads with stoplights and stop signs. What has been missing is a highway system at all that gets rid of the stoplight, stop signs, and other things that slow it down. And here we're talking about protocols, and that's why part and parcel of this whole discussion is actually the implementation of the parallel NFS and hyperscale, which are fundamentally what lets us separate metadata control plane from data and the data path. So we needed a new highway system because we had been working with legacy roads that simply didn't facilitate this. Um, it's like in a world of DNS, it's like if your DNS server had to proxy all of the traffic through just because it was the thing that could resolve the domain. That would not scale. Proxies suck. Well, the storage world, when you open the file foo, it had to proxy all of the access through to foo through that same means. So this is a very fundamental changing to the underlying plumbing or the underlying roadways. And that's why different class of thing from surface streets versus a superhighway system.
Yeah, that's very interesting. It's almost like now you can go up into the air and have any number of things moving at different heights, so they're not crossing over each other and
Mhm.
still getting to where they need to get.
Well,
That's very
it's not a coincidence. This is the same innovation that enabled software-defined networking, getting the control plane separate from the data path.
interesting. I had wondered
So
about that too. That's a very good piece of information because
mm,
software-defined networking, it's dynamic in nature, right? As
yeah,
as more requests are coming in, it's like, okay, let's scale out as need be, scale up, scale down kind of stuff,
that's because the
which
data can flow directly like it always has. The control plane is held separate and apart and able to overlay without killing your performance. You couldn't do that with storage, not through the legacy protocols. That's why this whole adding the abstraction layer, like allowing data to be orchestratable, being able to aggregate many different storage systems under a single pane of glass, under a single namespace, that will never work using the older protocols. It requires the parallel file system architecture borrowed from the supercomputing world, but applied through standards NFS to make it possible that NAS can now have that scale, and that's what we call hyperscale NAS.
yeah, I love that stuff, and I love that analogy, and let's bring in, speaking of parallel processing, Matthew Shaxted, and Matthew from Parallel Works. I remember talking to David a few months ago, and he explained what they had done, and I had this epiphany. I said, wait a second. I remember going to an HPC conference in Austin, Texas in like 2009, and I'd been in the world of big data processing for about a decade. And I'm walking all around this huge floor and all these vendors and all this activity, and there's no overlap between the worlds of HPC and big data processing. I'm like, that's bonkers. Like, why don't you guys talk to each other? Clearly, you could learn something from each other. And I think it's because HPC is very academic, it's a lot of life sciences and stuff like that. And so, those universities are an ecosystem unto themselves, and education
Mhm.
as an industry is sort of unto itself. But goodness gracious. And then when when David told me that, I'm like, dude, you're the first one I've ever talked to in all these years who figured that out. Took a page out of HPC's playbook and implemented it in the data world. I was like, congratulations. So, Matthew, what are your thoughts
Yeah, I mean
about all
that's
this?
yeah, I'm with Parallel Works. I'll give a little story, but you hit it exactly. I mean, HPC is, a legacy, fairly niche world. You go to these conferences, a lot of academia or organizations that can support teams of PhDs operating their own supercomputing class systems, and
Right.
it's been that way for a long time. What we've been seeing happen over the last few years, especially with AI and LLMs and all this different sorts of machine learning workloads going on, the same infrastructure tactics and experience from HPC are now being applied to these larger AI systems that are coming online now. And we're kind of in pilot world and beyond at this point. And what's happening is the shape of the architectures and platforms under these clusters is changing. You're going from maybe HPC systems that have, and these are still being built, but 20, 50, 100,000, 250,000 cores, and maybe a smaller set of GPUs on those. So it's HPC adjacent AI. And you have, researchers and, physicists running models there and physics-based models of different kinds, using machine learning to train the physics-based models and replacing the fundamental kind of physics computing going on. That is now shifting to, more like, oh, we're going to stand up a 4,000, 10,000 core GPU cluster. And those same networking requirements, the same storage requirements, which, I know David was talking some of that about, and we'll get into it more. The same fundamental topologies exist and the same experience can be applied in those worlds. So we're kind of seeing AI almost overtake HPC, or I'd say almost eat HPC.
Wow.
Large organizations that have HPC teams have been morphing into the AI teams, and it's been an interesting thing to see. Really over the last, I'd say, 4 years, I've been watching that happen.
Yeah, and that's, the other thing that I've noticed over the years is data science versus data management. And they tend to be very different worlds. Even in large corporations, you have a data science team, and they don't really talk to the data warehousing people. And I'm like, well, why
Yeah.
not? I mean, data is the lifeblood. It is the oil. It is a representation of the business itself. Why wouldn't you guys talk to each
Well, I
other?
think what you just described, that's like you have like the end users and then you have the infrastructure managers. And it's kind of similar to where Hammerspace and Parallel Works play together because we're kind of different sides of the same coin in a way.
Interesting.
David and Hammerspace was describing what they do at the data control plane layer and how they're orchestrating, data with this super highway and abstracting away the metadata from the actual storage. We're doing that same thing on the compute side. So for the end users that are actually running compute jobs and creating workloads and different pipelines, and that could be physics-based pipelines, it could be a lot more AI, LLM, machine learning-based workloads, object detection, whatever. We're working at the end user level, and we're abstracting away the pretty large differences that exist between these different platforms, computing platforms. And a lot of that, I call it like the scheduler layer, right? You have VMware and OpenStack and, older PBS, Slurm scheduler, LSF schedulers. These AI systems are using different schedulers, Kubernetes and OpenShift and whatever. And not many organizations are just moving to a single scheduler layer. So you need to be able to abstract that scheduler layer away so that when end users want to actually run computing jobs on where they want to, they don't have to completely change their entire mode of thinking. So we're trying to do that, which is similarities. Yeah.
Yeah, that's actually very, and I wasn't aware of that. That's pretty interesting stuff. So, I mean, you're basically talking about provisioning the data and then the compute, right? And of course, Snowflake did some really great work separating compute from storage. That opened up a whole bunch of doors. I thought their whole approach was very clever because they realized, look, standing up a data warehouse is a very time-intensive process. And in the old-fashioned way, I talk a lot about old IT versus new IT. We might get into that later on in the show. In the old IT world, you had to do your schema, then you load all the data, you got this big honking data warehouse, and then someone's like, "Oh, I want to change the schema." And they're like, "What? You want to do what? No, you're not going to do that at all. Like, just be quiet. Don't even say that again." Because you couldn't do that. So like, hey, how can we design a system where you can rip it down and spin it back up quickly? And that's what they did. And so it opened these doors of doing things new ways. But folks, don't touch that. That. We'll be right back. You're listening to DM Radio. All right, folks, back here on DM Radio talking all about parallel processing and parallel data movement and compute and storage and abstracting away the utterly painful process of dealing with heterogeneous information architectures and landscapes and topographies. And oh my goodness gracious, who doesn't hate trying to find some file somewhere or get some out? Where is that gosh darn thing? What these folks have done, I think, is absolutely fascinating. The company is Hammerspace and their partner Parallel Works. We were just talking to Matthew Shaxted before the break here, and Matthew, I keep wrapping my mind around how much efficiency is gained by being able to abstract out these different layers of complexity and enable people. Because let's face it, at the end of the day, if you're using software, you're looking at something, you're clicking buttons and typing on the keyboard, and the more you can see what's happening, the more you can envision how to improve things. And that's a big part of what you guys have done, right? And I've looked at some of your slides too, and you can see the workflows and the processes. And once that all becomes visible, and once you can abstract out the complexity of like when to compute and when to align with all the storage needs, like that just greases the track so people can get stuff done, right?
Yeah, I mean, I like to think of us actually as like the plumbers on the compute side, where the end users that are building these workloads don't have to think about the specific implementation details of the hardware they're running on. And, you said there's heterogeneous resources everywhere, and these, organizations' computing environments are becoming more and more complex. So that's going to continue. Quantum will have a chat GPT moment at some point in the hopefully pretty near future. And, organizations are going to start staging those in the same way that you're seeing GPU clouds being stood up as well. And so the layers used to interact with all these things are different. The people that want to do the work and the researchers and innovators and people building these pipelines, they don't need to get into the weeds of how to like run this on the top performing neural inference chip, right? They just want to see, take my PyTorch model and go run it over here. And so
Right.
we're trying to basically solve that problem. And what is interesting is data is a fundamental challenge in all of these type of workloads, state of gravity, moving it around. There's kind of old ways to do it, which involve the practitioners having to change the way that they're thinking. They have to stage data up and down to different
Right.
places.
Right.
This is where Hammerspace is kind of the glue that holds a lot of these heterogeneous resources together. It allows you to make the same namespace available anywhere. And that's why we're partnering so strongly with them.
Yeah, that's very cool stuff. That's a good segue to
Yeah.
Molly Presley, who hosts the Data Unchained podcast. That's how I first found out about you folks. Yeah, I was actually on your show, and that was a lot of fun. And I love that it's the Data Unchained as opposed to unleashed, right? Like one of the inadequacies of language is you wind up using the same word again and again and then unleash the power of it. Okay, unleash is my data a dog now? No, it's been
Yeah, it's a bit
chained.
more visceral to be unchained, isn't it?
Yes, it's like, okay, I don't want to be chained. I don't think anyone wants to be chained up. But yeah, tell us about your thoughts and what gets you excited about.
Yeah, definitely. So if you think about the conversations that we're having on Data Unchained, it really ties to your conversation, Eric, of old IT and new IT. The premise of the podcast is if you could know what all the data is that you have, whether it's coming off of sensors or the edge or different data centers, different clouds, and put it to use by the intelligence that wants to use that. That could be a GPU, it could be a data engineer, it could be a genomics processing application. What are the things you could do if you could feed all of that data to the intelligence that wants to take advantage of it? And so we delve into how are we doing things historically? What are new technologies and new solutions? And then what are the outcomes that companies are accomplishing with it? And it just ties so well to this conversation of there's really two key technologies that help in automating this. Instead of opening a ticket with IT to move data, you want software to identify what is the data, move it quickly and efficiently, and only move the data that you need.
Right.
But once you move that data, um, if the application or the compute or the user can't connect to it, it's kind of all for naught. So you kind of need to be able to identify and move data, but the applications and the workflow need to know where it is too. And it's kind of the holy grail of distributed workflows if you put these two technologies together. So it's super exciting to see the two coming together and have the opportunity for end customers to think about the art of possible with them.
Well, yeah, and you make a really good point here that there are these two planes. There's the data, that's the fuel that's used for applications, and every application needs data. Otherwise, what would it be doing? It's always processing something, whether it's structured or unstructured or whatever. So you got to get the data to the processor, and then to Matthew's point, orchestrating the compute side. I mean, that's probably as revolutionary as orchestrating the data side at scale to be able to dynamically manage those workflows. I mean, you figured it's kind of how the human brain works. A lot of these LLMs and trying to understand how they work has got me thinking about how my brain works and how we ingest information over time and persist information. And then you can trigger information by trying to figure out now where was that one thing I wanted to, and you kind of get stepping stones to it. But I keep thinking about that, and if you can optimize both of those realms, that's when you're hitting on all cylinders, right, Molly?
Yeah, absolutely. And then it's multiplicative because, or exponential really, that if it's just me saying, where was that one thing I wanted and how do I move it? That's a task. But if you have an organization or a bunch of compute nodes that don't even know what data was ever created, and you can also feed that, the data that other users created and other applications that you don't even know existed, then that's where it becomes really powerful.
Yeah, that's very interesting too. So, from the Hammerspace perspective, you will overlay on whatever information source there is, right? And so these are it's not an API, I don't think, but it's a connection to that you've created to give access to this hyperscale conduit that grabs whatever it needs and moves it to wherever it needs to go. Is that about right?
Yeah, we call it metadata assimilation, which is kind of a cool sounding technology. And it is actually cool. Our customer and partner over at Meta said it's like magic. And why he says that is they needed to become aware of a lot of data very quickly. And you usually think about the physical parameters of a data move or data copy across networks and say, okay, that's going to take days or weeks or months to accomplish that. With Hammerspace, it was seconds, milliseconds. It was in that realm. David will know exactly what it was. And all of a sudden, the data that existed in these different infrastructure silos was visible to the applications and researchers because it was just
Oh,
metadata that we were unifying. We weren't actually moving the
I
data.
see. I
And
get
so
it.
it's magical because all of a sudden you can see it. And then if you want to do something with it, that's all done through our metadata control plane and file system so that if the date file is moving or something else, it's you can't it's abstracted from the user so they can work with the data while it's in flight or moving or just leave it where it is and never move it at all.
That's very interesting. And I'm realizing now too, so through the metadata, that's basically what all these different endpoints can see now is all the metadata that's available. And obviously metadata is much smaller than the real data that you're moving, especially with movies
Exactly.
and audio files and things of that nature. But if I see where it is, then I can just go grab it and get it done. And that's basically what's happening, right? So, okay, I want to get these sets of files to be able to run this process. And it's like it sees, okay, they're over there, boom, bring it back in and do the processing, right?
Yeah, and just imagine the power. You were talking about data scientists and data engineers, even just for individual humans who are working with this data. They can now look at the metadata of this massive data set, not just the data set that's been provided to them, and
Interesting.
ask interesting questions about find me anything that meets these certain parameters or objectives.
See, that is so big in the data science world because being able to see all the possibilities, that's what gets the human brain kind of juicing and running on all cylinders is like being able to kind of play around. That's why I've always loved the discovery side of data science and data management, whether it's visualization or just being able to understand the topography, right? Like if you can, let's say you're trying to get across a city in a very quick little segment of time, if you can see from above where all the roads are, you can then walk your way all the way through. Whereas if you're stuck in a labyrinth, then you don't know. Can I turn left? Oh, that's a dead end street. No, can I go to here, there, whatever? That's kind of what you're enabling, right? It's that strategic view of what's out there. And from a data science perspective, that is tremendously enabling, right, Molly?
Oh, absolutely. In fact, I'm married to a data scientist, and so of course he knows about Hammerspace and what we do. And he's like, "Man, I just imagine the power." He worked as a data scientist at Amazon for ages, and you think about the number of objects when you're dealing with Prime delivery that they're dealing with. But he still was only allowed a discrete data set that he had access to, not Amazon Corporation.
Right.
And so what you kind of just imagine the possibility of your Ford motor and your data scientists can see the metadata of the data coming off the autonomous vehicles if they're granted the permission to do so, at the same time as they're seeing the research data of the manufacturing facility and pluck out the relevant data sets to do science. And it's a massive change in not just data access, but the kinds of insights you can derive.
Yeah, and David, I'll bring you back in. When you know your options, you can make better decisions. If you feel like you're constrained to, three possible options, that's just not as exciting if there are like 30 or 50 or 1,000. But you have to be able to see them and kind of understand them. And that's why it's so important to have this metadata abstraction layer, right? Because it's fairly easy to align metadata. What do you think?
Well, absolutely. And especially when we have proliferated so many copies of the same thing, just getting
Oh,
global
right,
visibility to that. And then the fact that now that
right.
it lives within a single namespace means I don't have to continue the madness of
Wow.
creating more copies of the thing.
Wow.
So yeah, you've hit the nail on the head. It's really about unifying the metadata from all of this distributed storage into one. And that allows you to have that global visibility, dedupe the whole thing,
Eesh.
uh, and
And
and avoid avoid making copies in the future because now data
right.
movement happens from within.
Yeah. Oh, that is so cool. And what's the stat? I've heard terrible stats of like 5, 6 copies of data are just all over the place. And it's like, if you don't have that strategic view, you don't know that. Someone put a whole
That's
bunch of
right.
storage over here. Someone backed it up over there.
And it only does you so much good to catalog all of it and find where all the copies are if you're still having to use the same copy, to move it around. You're doomed. Your inventory of the stuff is antiquated the moment it's done. That's why having the data movement happen from behind the single pane of glass and having that single pane of glass be the unified catalog of all of the data everywhere. That's the very important concept here.
That's
Logical
awesome.
unification of physically distributed data.
Wow. Logical unification of physically distributed data. That's very, very cool stuff. I'm going to throw a little curveball at you and see what you think about this. I've been thinking just recently about old IT versus new IT and what's the difference between these environments. And in one sense, I'm going to say old IT is imperative programming, new IT is
Mhm.
declarative programming. Would you agree with that?
Absolutely. Well, that is part and parcel to data orchestration, is that in a data orchestration world, it's through the declaration of service level objectives that you describe what the data needs from the physical infrastructure to exist. If
Right.
you think about it, data is the focal point. And yet, what we have managed has always been storage, and data was only indirectly,
That's funny.
managed by the selection of what storage to copy it into. That's the tail wagging the dog. But
That's
in a
funny.
world where data is orchestrated, you actually use metadata to describe, hey, this data needs to be super reliable. I need to have 5 nines. I need to have 10 nines. This data needs to be super performant, right? I need to have
Oh,
this many IOPS. And oh, this data needs to have sovereignty to these countries, right?
wow.
So you express in a declarative fashion the constraints about how the data is to be rendered onto the infrastructure. And then the orchestration system applies that. So I think you have nailed it on the head here. Modern IT, the new IT is declarative. Kubernetes is declarative. You say what those containers need, and it will determine where to instantiate and run them to have the right capabilities. So it's the exact same thing, whether you're orchestrating the containers, container orchestration, or whether you're orchestrating the data. It's a declarative model. That's the
Yeah.
big difference. Imperative versus declarative. You hit the nail on the head.
That's very cool. We got about a minute and a half left in this segment, so I'm going to throw another one over at you. In the development world, a lot of folks keep talking about shift left, and I'm gonna tease this up for the next
Mm,
segment. And basically, shift left really means go further upstream in the process and workflow and technology to solve a problem way upstream, so it doesn't wind up going downstream.
that's right.
And,
Yeah.
shift right is like, okay, let's focus on the business applications where people are actually using. We'll put some checks in there because we're going to talk about data governance, for example, but we're also going
Mhm.
to talk about optimizing the flow of information. And I remember when I talked to you the first time, you told me that you went out and grabbed a couple developers from the Linux kernel to work on this stuff. And I'm going to throw this out there for us to think about in the next segment. You can't shift any further left than getting
That's right.
into the operating
Well,
system.
this we have to talk about next because what we're really talking about here is functions of the operating system, process scheduling,
Right.
data supply. These are file systems and
Right.
virtual memory subsystem and process scheduler. But we're talking about doing that at the massive scale, parallel and heterogeneous across whole data centers. And so what we're really talking about here is the operating system or operating environment
That's
for the modern parallel heterogeneous world.
that's amazing. We'll be right back, folks. You're listening to DM Radio. All right, folks, back here on DM Radio. Fantastic, fascinating show. Get me to the GPU on time was the title I came up with, and it's just kind of a fun way to think about the fact that you have to get to the processors because they're the things that actually do the stuff. They process the information. And David Flynn of Hammerspace, I'll throw it back over to you. Like optimizing the OS is pretty cool stuff, especially being able to do so at scale in a parallel world, right? When you're doing this parallel processing, you have to think through all the intricacies about what it's doing. I'll throw a quote over at you from Dr. Michael Stonebreaker, who I've had on the show multiple times, the godfather of the modern database, or at least the godfather of Postgres, Ingress, and all that kind of stuff, Vertica. Tamer. He's got a bunch of companies. He said something to me. This is probably 7, 8 years ago. He said, 80% of the code that's ever been written should just be thrown away. This is how he described it. Because he was talking about the fact that you had these older architectures and that
Yeah.
systems were designed for spinning disk, for example. Systems were designed for certain limitations that are now not around anymore. So, being able to optimize the operating
Yeah.
system, especially at scale, that's hugely important. It's very complex stuff. Like,
Well,
what do you know about it?
Well, this is what I did at Fusion IO, my previous company. We introduced the high performance modern SSD, what became NVMe. And
Oh,
what I did there was I went and recruited the Linux kernel maintainers of the block IO stack, uh, folks like Jens Axbo and Chris Mason. And we basically cleaned out the cobwebs down at the heart of the Linux kernel
that's
to
funny.
allow the kind of crazy performance levels that you can get from Flash because those systems were designed for disk drives. And,
Right.
basically our whole premise was Flash should go upstream, talk about shift left, upstream of the disk controllers, buses and protocols, and even whole storage arrays, and Flash should go directly on PCI Express. And thus was born NVMe. Well, that
Wow.
team, that my Linux kernel team that was helping clean out the block IO stack in Linux, they've all landed now at Meta. And that's when I went on to found Hammerspace and work
Oh,
at the file system level, the next level up. And we recruited Tron Mickelbust, our CTO, who's the kernel maintainer of the NFS stack. And all of this is to clean up how data is delivered through at the logical level, the file system level, and shared across the network, because those are the things that are very hard to do at these crazy performance levels that Flash makes possible. And that GPU
right.
computing now demands. So we finally have a supply and demand side match between what NVMe can supply and GPU demand, but we've had to clean up the file system level within Linux and within the standards protocols. And all of this is because, at the heart of the OS is really the two pieces, the file system and supply of data, and the processing and the compute side, the virtual memory subsystem, and other things that do the job scheduling. And that's why this partnership with ParallelWorks is really a match made in heaven. We're all about orchestrating data and the data operating environment at the full multi-data center scale, and they are all about the compute, distributed compute at the multi-data center scale for that operating environment. So it's no longer about the OS on one little system. It's about the operating environment across many systems and even across whole data centers. And that
Right.
operating environment has never really been fixed to work very well, up and down that stack.
That's very interesting. It's actually a good segue too to bring Matthew back in. You want to align these things as tightly as possible, like gears. When gears come together and do stuff and push things through, they have to be aligned. If you get a wrench in the works, that's what breaks machines. So this union of Parallel Works and Hammerspace, I think is very powerful because you're each aligning one of those big gears and getting them to move perfectly through and do the workloads, right?
Right. Yep. And as David kind of said, it's moving up the stack from the OS level now into, global multi-data center environments. And it's kind of making that possible. You mentioned about that quote about throwing away 80% of the hardware too, and
Right.
new versus old IT. And I think about that, and that'd be amazing to do that, right? And have organizations start over from where they're at today. But and most will agree, and not all the time, but that's generally not going to happen. There's
Right.
legacies of different ages of hardware that are on multi-year refresh cycles that are always staging in and introducing new things, and they'll be there for 3 to 5 years, depending, or even less, depending on the organization requirements. And so it's also about how to, for us, it's how to transition organizations to these new architectures in a way that doesn't totally disrupt, what their end users are actually doing. You brought up Snowflake as a good example, and there's a lot of these data platforms out there that are, and especially AI platforms that are proposing to do things in an amazing way, but it requires a pretty big upshift and architecture changes on the infrastructure side to be able to even adopt that. And
Right.
and this is where I go back to the kind of scheduler layer. There's legacies of these different interfaces to the infrastructure that have existed for decades in some cases. Along with those, there's sometimes decades of institutional knowledge in the form of like scripts and
Mhm.
software codes and binaries or whatever that run in certain ways. And, in a lot of places, Fortran is still very much, required and needed. And yeah, everybody would love to move to Go or some other, more modern, but it's just not going to happen. And the people that wrote that software in many cases are gone, right? So it's about how to transition people into these new diverse environments in a way that can be manageable for the people managing the environments, and
Yeah.
it's,
Yeah. And we've got about 4 minutes left in this
Yeah.
segment. Real quick, how much knowledge do you have on different OSs, different environments, different types of compute, for example? I would imagine you've got a lot of experience seeing the performance of this versus that, and
a lot.
knowing just knowing what the hardware is and how it operates and what's its sweet spot, right?
Yeah, and I mean, in our team spends years tuning things to get maximum compute performance out of the different environments we run in. And
Right.
if an organization is an AWS shop and they're trying to repatriate back into their on-prem environments, and moving into like OpenStack or something, you need to hit certain performance requirements that match it. So for us, it is going kind of all the way down into the looking at every single thing that's starting up on a node and booting and what's actually needed on the node. So we do get that down to that level as, GPUs and the, diverse CPU architectures are coming or then coming on, and you have all the clouds creating their own ARM-based infrastructure or platforms. Everyone is pretty diverse on the needs, different driver requirements. Every cloud we operate in has different HPC tunings that need to be
Right.
applied,
Right.
different networking stacks.
Right.
So it can easily take what a existing sysadmin team is currently operating. And if they want us to, hey, we're going to bring in Azure now.
Right.
And we're going to run on Azure's InfiniBand, and we heard it's great. I mean, the amount of work you need to actually get that thing performing really well to a
Right.
level that is comparable to an on-prem system is vast. Like you're
Yeah.
bringing in Azure HPC experts. So we're trying to remove that. Yeah.
Well, that's a very, very good point too, because a lot of people think, all right, in the cloud, it all runs perfectly in the cloud, right? It's like, no, it doesn't all run perfectly in the cloud. There are different architectures that they have, different layers of abstraction, different ways to the hoops you have to jump through basically to get that. And that you also have newer machines in these cloud environments. I remember Teradata bragging years ago about how they were going with Microsoft instead of Amazon because Microsoft had newer servers and it was going to go faster and all this stuff like that. I'm like, all right, well, I can see that that would make sense, if you get the new servers and they're, now you can order and say, okay, I want the new GPUs or the TPUs, the Google TensorFlow processor Unix. And these are all very different things that have their own signatures. And to your point, Matthew, you got about a minute left. It really pays to understand what this does versus what that does and how to align those things, right?
Well, and that brings in the value of agile task placement, and being able to move things around without being tied or locked into one environment.
Right.
And you brought up, I wish you can go to the cloud and everything just works for the type of workloads I'm running. But I have the analogy that, they give you the individual car parts. You have to go and actually assemble the car
Oh, wow.
into what you want to use. And yeah, they come out with a new engine, that is great, but you actually need to assemble it into the type of thing you're trying to run, which for us means a cluster of VMs all working together to solve one problem in some cases, or a
Interesting.
GPU cluster that's training and, you're running TensorFlow distributed or whatever on it. So yeah, I wish it, was a little more seamless, but that's the value we're providing.
That's right. You don't want to abstract away your own value add here, right?
I mean, honestly, it wouldn't be the worst thing if the clouds just would do that, and they're starting to. I mean, Amazon just released their managed Slurm product, but anyways,
Right.
yeah.
Well, folks, we'll be right back with the podcast bonus segment. You're listening to DM Radio. All right, folks, time for the podcast bonus segment here on DM Radio, talking to Hammerspace and Parallel Works, and a fascinating show because it's fascinating technology. It's just so cool. I love when old intractable problems are solved and you're like, yay, I don't have to do that anymore. And David, Flynn, I'll throw it over to you. Now, this is not an old intractable problem. It's a very new problem. Training LLMs. That's something that you folks are actually doing on Meta too. How the heck do you do that? How do you train a large language model?
Well, to be honest, large language models don't need a lot of data per se. Language is highly compact. It's when you start going multimodal that things get really interesting, because now you have the need to feed this rich media in mass. And so
Oh,
so that's where the real challenges start, is training, generative AI type models that are observing video or photographs or other rich media, audio, and learning from those. In which case, you're feeding that thing. I always come back to this. I was watching this the other day with my young kids. The movie from the '80s called Short Circuit.
oh
There's a
yes.
part there's a part where it's observing, all the stuff on TV or whatever, and it's like you got to feed these massive feeds at just as fast as they can go. It's the thing about AI is it is not bandwidth limited like we humans are, as to how quickly we can absorb information through eyes, through ears, etc. That it's as fast as you can slam it through the GPUs, at massive scale.
Oh,
And that
interesting.
gets really interesting when it's rich media and not just text, because going
Right.
through the whole corpus of text on the whole internet isn't very large in comparison.
Wow. And I'll throw one more question at you and then throw it over to Molly to kind of close us out. The aha moment I had with large language models was when I realized that when you are training, when you're feeding them new information, like let's say it is text, it's not persisting the text exactly like a string like you get in a database. What you're doing is you're adjusting the weights and the biases
That's
in
right.
the parameters. And of course, these
Correct.
models can have any number of layers. You can have hidden layers. You can have all sorts of
Hmm.
different
Hmm.
things. And Llama is open source. OpenAI, we told before the show, should now be called closed AI because they closed that box. Now it's a black box,
That's right.
which from a regulator, from an auditing perspective, is a nightmare. So
Hmm.
it's very interesting that they made that decision, but I guess it's proprietary. But to me, that was the aha moment. It's like, wow. So it is always going to be probabilistic, and that is an issue for deterministic
Hmm.
use cases, but it's really interesting what it can learn, like what it can figure out how to do all kinds of different patterns, right?
Well, yeah, it's extremely flexible. Learn how to fold proteins, learn better how to predict the weather. What they're finding is that these very general purpose functional forms that, deep learning, the weights in a neural network allow it to approximate real world phenomenon better than, the scientific formulas and finite element analysis and other things. Those just explode in complexity and kind of miss the broad generalities. And the thing about these models is they can learn the broad generalities very quickly and become quite good at it.
Wow. Molly, final closing thoughts from you. How do you train LLMs? One
Yeah,
one
sure.
bite at a time?
I think that one of the interesting things, I'm in the marketing space and I look at the marketing around LLMs and the infrastructure and the data side of it a lot. And there was such a huge focus there for a year or so on really fast data paths to GPUs. And of course that matters. But the much more difficult problem is how do you get distributed data to GPUs? It's sitting in a lot of places and it needs to be orchestrated to the GPU because maybe you can't buy any right now. Maybe you just want to rent them for a couple months from NVIDIA Cloud or AWS or whoever it is. And a lot of organizations know they have data. They want to get that into an LLM, but they don't own the LLM infrastructure and where it's running. So the conversation is really shifting on the infrastructure side to not so much be focusing on just how fast can you feed a GPU. Of course, that matters. You want to take advantage of them, but the data orchestration side, we're seeing this in research coming out from NVIDIA. We heard at a government conference hosted by them just recently that the orchestration of data to the GPU is the really unsolved problem. It's solved by Hammerspace, but that's something we need to make sure everyone knows about. And
Right.
so thinking about LLMs, I just would go back to there's finding the right data and then getting it to the GPU, and then of course feeding it very quickly is where the conversation seems to be shifting right now.
Yeah, and optimizing the workflows and the efficiencies, and maybe I'll give a last comment to Matthew Shaxted. The fact that you are optimizing the compute side of this equation is really very, very important to understand which, because it's just like people are good at doing one thing, other people are good at doing others. I'm not very good at basketball. Some people are good at basketball. So knowing which hardware is better at which use case is really valuable stuff and allows you to dynamically optimize the efficiency. Because let's face it, you look at the amount of energy being used by some of these things, and it's just kind of off the charts. They can't even build. What did someone tell me? They built a data center out in Utah and they can't even use it now because there's not enough energy. They're like, oh, sorry. Oops. So it's really good to fix both sides of this equation, right, Matthew?
Yeah, exactly. I think having systems that begin to help the practitioners, the people building these pipelines and then operationalizing, help make decisions about where to run is kind of the next big frontier, at least for us, where, right now it's very explicit. They choose where they want to go and you run your task on this GPU cluster or this cloud or whatever. And to your point, having a system that can now make the intelligent task decisions with the practitioner or eventually for the practitioner is kind of that next frontier for things like power performance. It knows at this time, it's getting hydropower. You can send it over here and it's going to be the best, power performance for you versus, this time we're going to move it over to, cost performance. So setting policies and then being able to drive actual compute task decisions is kind of a next frontier for us.
Well, and understanding multi-cloud. So I joke we went from hybrid cloud to multi-cloud in like 2 weeks when people figured out, okay, it's not just on-prem and this one cloud, it's on-prem and all these different clouds. And being able to see into those environments and understand what's working well, where and how it's working, all this observability stuff, which has just blown up in the last few years.
It's funny you said that because I literally, really before this year, I've had it's a lot of organizations are like single cloud.
Right.
And they were like, they're the Azure shop or the AWS shop, and then they're hybrid. So they have on-prem and cloud and single cloud. I've never heard multi-cloud used as much as I have this year, where because of these technology, improvements, and Azure's putting this on the floor first, or Google has this specialized infrastructure, and then the whole host of tier 2 providers that are providing, specialized GPU clouds.
Right.
Now you need to become multi-cloud, and that's great for what we're doing because it's what we try to enable. Yeah.
Well, folks, what a fantastic show today. Big thanks to all of our guests, David Flynn and Molly Presley of Hammerspace. I love that name too. And Matthew Shaxted of Parallel Works. Look them up online. Send me an email if you want to be in the show, info@dmradio.biz. We'll talk to you next time. You're listening to DM Radio.